So I'm going to move on to a different topic to try to first explain the large sieve, and then we'll see how that fits in with the Bombieri-Vinogradov theorem. So if you do have questions on the Selberg sieve, this would be a good time to stop me and ask. Fine? Okay. So Demetrius in his lectures was talking about primes and arithmetic progressions, or if you count it with this logarithmic weight, the von Mangold function, then the theorem is that this is asymptotic to x over phi of q, and we expect this to be true uniformly in a wide range of values for q. And we would like to prove some result like that this is true with some error like x e to the minus c root log x. Right? So if q is 1, this would be the prime number theorem, and that's certainly something that you can prove. Okay? Now, the trouble with this is that we don't really know how to prove this result. So firstly, this result is only good if q is a little bit smaller than e to the c root log x, right? Because the main term becomes smaller than the error term if q is very large. Okay? But even this we don't know. So even this result, so this is, only good if q is less than, say, e to the c root log x. But in fact, it's a little worse than that. It's only known if q is less than some power of log x. And this has to do with this problem of Siegel zeros, based on what we know about something called Siegel zeros. Okay. So this is the Siegel-Wallfisch theorem that Demetrius was explaining last time, on which I think he'll finish off today. Right? So I'll recap that after Demetrius does it when we need it. So anyway, so the upshot is that even though you expect on the Riemann hypothesis that there should be an asymptotic formula for the number of primes in a progression, all the way for q up to a power of x, like x to the half, we only know that for a very small range of values of q, only going up to some power of log x. And even if you were very optimistic and there were no problems with Siegel zeros, the classical proof would only allow you to take q to be like e to the c root log x, which is still smaller than any power of x that you want, but larger than this at any rate. Okay? So the Bombieri-Vinogradov theorem, which has been mentioned a few times already, so I just want to state it today. It gives you some kind of asymptotic formula for the number of primes in a progression, but on average over q. Okay, so we take all arithmetic progressions a mod q with a coprime to q, and let's look at the remainder term psi xqa minus x over phi q. Right? This is the object that we would like to say is small. And we don't know how to say that this is small for each value of q, except in some very limited ranges. But we can do better if you sum over all values of q. Capital Q. And the theorem will say that you can make this be smaller than x divided by some large power of log x. provided q is smaller than square root of x divided by log x to some power. So for any a that you like, let's say 1,000,000 is good enough for most things, then you can get x over log x to 1,000,000 so long as you stop a little bit smaller than root x divided by log x to the billion, let's say. Okay? So what does this theorem mean? So if you knew the Riemann hypothesis, then this theorem would be pretty easy, because you would be able to say that this max for each value of q, the Riemann hypothesis would tell you that this is bounded by square root of x, maybe with some logs. So what we are summing would be the sum over q up to q, square root of x times log x squared, let's say. That's what the usual proof of things involving the prime number theorem in arithmetic progressions on RH would give you. And then if you sum this up, this would be root x times q times log x squared, which certainly if you want to make this less than x over log x to the a, you can do that by just choosing b to be a plus 2. Right? So b equals a plus 2 is fine. On the other hand, it's also good to record what the trivial bound is. Well, for example, you could use the Brun-Tishmarsh theorem that we discussed in the last couple of lectures, or even just take a trivial bound. The number of primes that are in a progression a mod q is no more than x over q. Right? The number of integers in a progression a mod q is no more than x over q. Okay? So this parameter, whatever it is no more than x over q maybe times a log x. So the trivial bound would be something like q goes up to q, x over q times some log x, which when you sum up gives you something like x times log x squared. Okay? So in this sense, the Bombieri-Vinogradov theorem is not asking for anything too ambitious like the Riemann hypothesis. It's only asking you to save some large power of log over the trivial bound. Okay? But it's actually a very useful result. In practical applications, it's not like you've just saved some large amount, some smallish amount over the trivial bound. It feels like you're playing around with something where you know, like the Riemann hypothesis on average. Okay? So this can be thought of as GRH on average. Now, let me make one more comment. In his lectures, Demetrius also mentioned Montgomery's conjecture. So if you recall, that was something which went beyond the Riemann hypothesis. It gave you an error term in the prime number theorem in arithmetic progression, which also included the fact that, that if q gets large, there are smaller and smaller numbers that you have to consider in your progressions, right? So instead of just giving you the GRH bound, which tells you that this remainder term is bounded by x to the half plus epsilon. Montgomery's conjecture gave you something like psi xqa is x over phi q plus an error of, let's write it as x to the half plus epsilon divided by square root of q. Right, so the new bit is this square root of q in the denominator. Okay. If you now assume this conjecture, then you can see that in the Bombieri-Vinogradov theorem, if you now put this error term, over root q. So you gain this 1 over root q here. So this would be x to the half plus epsilon times capital Q to the 1/2. Right? And so you can see that you can make this be smaller than x over log x to any power a that you like. I could just have written x to the 1 minus epsilon here, but let me just write it this way so you can see the similarity with Bombieri-Vinogradov, so that you would expect that this is true, that this holds so long as capital Q is no more than x to the 1 minus epsilon. Instead of going up to root x over some arbitrary power of log x, you can even go up to x to the 1 minus epsilon and get cancellation on average in the primes and progressions. Okay? So this is quite a powerful conjecture, and this is known as the Elliott-Halberstam conjecture. So to tie this up with the other courses, so what James will speak about on the work on bounded gaps between primes, that uses as one ingredient the Bombieri-Vinogradov theorem. So in fact, after James's refinement of the original GPY argument, it turns out that you don't actually even need this Bombieri-Vinogradov theorem with q going up to square root of x. Even q going up to x to the 1/10 would have been enough for that, for the new work on gaps between primes, which is remarkable and unexpected. And then they also have other results which give you better gaps between primes if you assume something like the Elliott-Halberstam conjecture. So if you assume the Elliott-Halberstam conjecture, you can get the closest to twin primes, and you can show that the gaps between two consecutive primes are infinitely often smaller than 6. So that's what these conjectures allow you to do. So my goal in the next several lectures is to give a proof of the Bombieri-Vinogradov theorem. Oh, I should say one more thing. Before Maynard's work, there's the other way to get bounded gaps would be to try to improve the range of application of the Bombieri-Vinogradov theorem. And this was the achievement of Zhang. He didn't achieve this with all values of q, with all moduli going up to q bigger than square root of x, but he was able to take a special subset of the integers up to q called smooth numbers, which we discussed a little bit yesterday, day before yesterday. And then for that subset, he was able to take q to be a tiny bit larger than square root of x, x to the half plus delta for some fixed delta positive, and then that was enough to get bounded gaps in the original approach. So Emmanuel will discuss a little bit about Zhang's theorem and also the kind of things that go into Zhang's theorem, which are very different from the other classical inputs. Okay. Now, there are kind of two main things that go into the Bombieri-Vinogradov theorem. One ingredient is the large sieve. And the other is the Siegel Wolfish theorem. So the second ingredient Dimitris was discussing yesterday, and he'll finish off the proof of that today. So we will recap that maybe at the very end if we need to. And what this allows you to do is to, basically this is needed for small values of Q that you have to handle, and then the large sieve is the driving force for larger values of Q in the Bombieri-Vinogradov theorem. It's not strictly speaking correct, but roughly you could think of it that way. So I want to start by explaining the large sieve part of the argument today. Okay, or explaining the large sieve today, and then we'll see how it ties up with primes and progressions maybe tomorrow. Okay. So the large sieve is going to be a little different from, at least initially, from the sieve that we've discussed so far, the combinatorial sieve very briefly, or Selberg sieve, in that in the large sieve you don't first see any set, or you don't see any set that needs to be sieved. It's really just an analytic inequality that we're going to work out. But then I'll explain why this analytic inequality can be thought of as a sieve in a certain sense. So what does the large sieve deal with? So you imagine that you have some numbers an. These are complex numbers, arbitrary. And we're going to form this exponential sum and here I'm going to write E of x to be e to the 2 pi I x. Okay, so this is some oscillating function. I don't know much about these ANs, but if they were kind of some random object, I might think that for most alpha, maybe this guy will oscillate around in such a way that these things roughly cancel to, say, square root size. Okay, so you should think of, let's think of AN being of size 1 usually, so that a trivial bound for this might be like n. Okay, so the trivial bound is and the hope is that usually S alpha is bounded by something smaller. Maybe it has square root cancellation, and you get something like n to the half plus epsilon. Okay? So, of course, this cannot be true always, right? For example, if the ANs were all 1, and then alpha was equal to 0, then there is no cancellation, and you're just summing 1 all the time, and you get n. Okay? So this can never be always, but only usually. Now, one way to think of why you get this square root cancellation usually is just by computing the L2 norm of this exponential sum. This is just Parseval's identity, and you see that this will be equal to the sum n up to n an squared. And if I'm thinking of the ANs as being typically of size 1, then this is typically of size n, maybe, capital N. So that suggests that at least the measure of the set of alpha for which this is bigger than, let's say, 1,000,000 times square root of n, well, the measure of that set is no more than 1 in 1,000,000. Now, what the large sieve wants to do is to take some number of points, let's say m points, alpha 1 to alpha m, all in, let's say, 0 to 1 or r mod z. The function S alpha is periodic with period 1, so I don't have to worry about translating by integers. And I should assume something about these points. So I'm going to assume that I'm not picking the same point many, many times, right? Obviously, if there's a point, like let's say if the ANs are all 1 and then alpha is close to 0, if I pick values near 0 all the time, then it's going to be true that for all of these values, this function S of alpha is going to be big. Okay? So I'm going to assume a spacing condition that these are delta well spaced, which means that if I take the distance between two numbers alpha j and alpha k, and this means the distance from the nearest integer, so that I'm thinking of the distance on r mod z, right? So this is the distance from the nearest integer, and this is always as large as delta for all j not equal to k. Okay. So let's assume that I'm given well-spaced points alpha 1 to alpha m satisfying this. Then the theorem says I want to give an upper bound for this quantity. And what should the upper bound capture? It should capture that typically it should be bounded by something like square root cancellation. Okay? So square root cancellation means, that the square of it should be comparable to this guy, which is the average of the square of S of alpha. So I'm going to compare everything to this object, n up to n, mod a n squared. Okay? So it should be some inequality comparing this to that. And I need to put a couple of escape clauses because I don't know what the ANs are and what the alpha j's are. Okay? So one thing that could happen is that there could be one value of S of alpha where all these quantities are all pointing in the same direction. Right? I can never avoid that. Is that okay? So, for example, if the ANs are all 1, alpha is 0 would be that quantity. Right? So, if I just had this sum here with absolute values here, I could use Cauchy's inequality, and Cauchy-Schwarz would say that the sum of the absolute values of AN would be bounded by, if I square that, it would be bounded by n times the mean square, the sum of mod a n squared. Okay? So my upper bound is going to have an n here, which captures that feature, that there could be one value of alpha for which all the terms that I'm summing are all pointing in the same direction. Okay? And then once I account for that, I want to say that then the values are genuinely different from each other, and then the mean square of this is just bounded by that. Okay? So if I believe that, then I have m quantities here that I'm summing, and I should just say something like n plus m times the sum of mod a n squared. Right? That would be square root on average. Except that I have to make some assumption on what these points are. For example, as I said, you don't want to choose the same point over and over again. So instead of putting n plus m times this, what would be natural would be to put something that depends on the spacing condition delta. Right? Now the spacing is, if you have m points all lying inside 0 to 1, there should be 2 of them by the pigeonhole principle that are at most 1 over m apart. Okay? So the inverse of this might be a reasonable quantity to try to put here. Right? And if they are all exactly evenly spaced, then you would get the kind of result that we want, which would be n plus m times this average. So I'm going to write this as plus this, plus something like big O of 1 over delta. One can be a little bit more precise. The big O constant is actually just 1. So you could write it as n plus 1 over delta if you like. And that will be true. Okay, so there's a few different ways of proving this. Okay, and I'll prove. I think I will not prove this, but I'll prove weaker versions of this in 2 different ways. Okay, and neither one of them will, beats the other, but they both will give you the flavor of the argument, and both are good enough for anything that we want to do. Now, so let's think of the proof. So what I want to estimate here is this kind of sum. J goes from 1 to m. What do I have here? Let's say n goes from 1 to m. Something like a n e of n alpha j, and the quantity squared. Let me make this m, let's say, just for fun. Right? This is what I'm going to estimate.
Sorry, is that capital M? Capital M?
This one? Little m. It's in script. So, and this one was kind of yeah. I can put some more curly cues here, something. Right? Or I could write so small that you don't see it. So, well, my notation is going to be all over the map. So let me, just to say what I want to say, right? So this was a capital A of n that I had initially. Let me replace this capital A of n by x of n, if you like. Okay? No big deal, of course. Right? And just so I can think of these guys, I can think of them as, let's say, A m n, which is E of n alpha m, let's say. Right? So you can see that what I've done here is I can think of now a matrix A, which is an m by n matrix, whose mnth entry is this exponential. Right? And then what I have here is that I take this this matrix A, and let's see, it's a m by n matrix, so I can multiply it by the n by 1 vector of the xi's. Right? So this gives me, so this is a matrix, so it's a map from Cn to Cm, right? So what I'm evaluating here is the vector AX, and then I'm computing here the norm of the vector AX, right, or the square of it. And so what we are interested in the norm of the vector AX squared, right? Now, another thing that I could consider, and what I'm trying to prove is some bound for this in terms of some object times the norm of x squared, right? So you could say the large sieve is an estimate of this type. Okay, so okay. Now, there are a couple of related things that I could consider which will allow me to change the problem. So this is a duality argument, and they'll allow me to change the problem to an easier one that I can just write down the answer to. So the dual things that I could consider are, I could consider some vector y in, let's say now Cm, right? So x is in Cn, y is going to be in Cm. And then I could consider, instead of bounding the norm of Ax, I could consider the inner product of Ax with some vector y, right? And I could ask to give a bound for this. Okay? So I could try to say that this is bounded by something times the norm of Ax times the norm of, let's say, norm of x and the norm of y. Yeah? Or the third thing that I could consider is the dual problem. I could think of the adjoint of A. So conjugate transpose. The conjugate is not necessary. Just think of the transpose if you like. It doesn't make any difference. Times y. And then bounding this in terms of the norm of y. Okay. Now, the point is going to be that, well, these three problems are, of course, closely related to each other, right? So if I had this inequality here with some delta squared, let's say, right, then I could just use Cauchy's inequality here. Okay? This will be bounded by the norm of Ax times the norm of y. And then the norm of Ax will be bounded by delta times the norm of x. So this will be true with the constant delta. Right? So this goes to, from here to there, is just Cauchy-Schwarz. Okay? How do you go from here to there? If you know this inequality, can you prove this inequality? Yes? You just choose y to be Ax, right? This is just Ax squared, and then this guy will just give you x times the size of Ax. One Ax will cancel out, and you will get this inequality. Right? So what we've proved is that if I call these strings 1, 2, and 3, which I should have remembered to write while I was here. So 1, 2, and 3, So the same delta here. So 1, 2, and 3 are all equivalent to each other, right? Or just in words, the norm of some operator is the same as the norm of its adjoint. Okay. So therefore, I can, if I think of this duality argument, I can rewrite my result on the large sieve. So I want to understand, so let's write this out in detail. So m goes from 1 to m. Let me just go back to my a's and alphas as I had there in the large sieve. So n goes from 1 to n, an e of n alpha j, alpha m squared, right? I want to say that this is bounded by something times the sum of mod a n squared. Right? And this is the same as saying that I can look at the dual problem where the n's come on the outside and the m's go on the inside. So let's give this a different name. Let's call it Bm. These are the y's, if you like, in my previous argument. And then the same guy here, E of n alpha m, quantity squared, is bounded by the same thing times the sum of mod Bm squared. Is this okay? So far, so good? Okay. So I think I have a new theory for how to use these blackboards. We'll see how it goes. All right? Okay. So now why is this problem easier? Well, what I can do is just expand this guy out and then see what I get. Okay? So if I expand it out, then I get a sum over two parameters, m1 and m2, bm1, bm2, maybe conjugate. And then I bring the sum over n inside, and then I have here a sum over n goes from 1 to n, E of n times alpha m1 minus alpha m2. Right? This is just expanding out the left-hand side of this board here. Okay? And now the point is that I can just evaluate this guy because it's just a geometric progression. Okay? So let's note that if I take the sum n goes from 1 to n, E of nx, then this gives me, okay, I guess I have to do it. Right? N plus 1. Yeah. Okay. So now, what can we say about this? The numerator, so firstly, this is always bounded by n, because it's, that's the most it can be when x is 0. So when I say bounded in absolute value, I can also say that the numerator is no more than 2, and the denominator is like, well, if I multiply by e of x over 2, I think, or e of minus x over 2, the denominator is like sine of, so the size of this is twice the sine of pi x. Okay. And that's roughly like, so this is very small if x is close to an integer, but otherwise it's not too small. Okay? So the bound here is that this will be bounded by some constant divided by the distance of x from the nearest integer. Otherwise. Okay? So now what can I say? Well, if I just try to use that in here, I'm going to get from the terms m1 equals m2, so these terms give you, so in these terms x is like 0, so I can't do anything more here. I'm just going to take the bound n. So that gives me n times the sum of b m squared. Right? So that's one of the terms that I'm going to put in here. It'll be n plus something. Okay? You can see the theorem in the factor in the theorem as well. And what if m1 is not equal to m2? Then I get something like the sum over m1 and m2 not equal to each other, going up to m. Let me put absolute values everywhere. I don't know anything about these coefficients Pm1. And then what I have here is the distance between alpha m1 and alpha m2. Right? Okay, now if I just use something simple like Cauchy's inequality, which will tell me that bm1 times bm2 is bounded by bm1 squared plus bm2 squared, divided by 2 even. Okay, and then there is symmetry, so I can just say I sum over the bm1 squared and forget about the bm2 squared by symmetry. So this is the same as the sum over m1 bm1 squared, and then what I have is a sum over all m2 not equal to m1, and then I have here 1 over the distance between alpha m1 and alpha m2. Okay. Now, so far I haven't made any use of well, I have to use this condition that the alphas are well spaced, which I haven't used so far. Okay. So now we know how to use it. Well, I have my alpha m1, which is maybe here, right? Then I have the two things that are nearest to it, and then two things that are nearest to that, and so on, right? And these two guys are separated at least by delta. These two are separated at least by 2 delta, 3 delta, and so on. Right? So there are only 2 things that are on the scale of delta, 2 other things on the scale of 2 delta, etc. And that's the worst thing that can happen. Yeah?
What if we start all the way at the bottom of the interval, we have something close to the top? Now the distance between them is close to 1.
No, so you actually, so this is why you think of the distance between the nearest integer, right? So it's a wraparound distance. Yeah? So so the distance between 0.1 and 0.9 is 0.2, not 0.7. Because you take, is that okay? You think of them on the clock or on normal t. So let me write it down here that the distance of x is the minimum over all integers n of x minus n. Is that good? So 0.9 and 0.1, the difference would be 0.8, but the distance between 0.8 and the nearest integer 1 is 0.2. Okay. Anyway, even if that didn't work out, I would be off by a factor of 2. And we shouldn't be keeping such precise score. But I think everything is correct so far. So now what? So you can see this guy, there will be 2 terms for which this could be as big as 1 over delta. There will be 2 terms for which it could be as big as 1 over 2 delta, and then 2 terms for which it could be as big as 1 over 3 delta, and so on. Right? So therefore, my bound is going to be, resuming from there, it's bounded by something like the sum over m1 bm1 squared times what I just said. So it will be something like, there will be some parameter k that goes from 1 to at most m certainly, right? Because there are only m terms that I have to worry about. And what I get is something like 1 over 2 divided by k times delta. This okay? 2 things spaced delta apart, 2 things spaced at least 2 delta apart, etc. So this is bounded by some constant times 1 over delta, and I've got here actually a log of m extra. Is that okay? So apart from this kind of log m factor, I've basically proved that result for you. Now, let me also make one more observation. I also said that delta is no more than 1 over m by the pigeonhole principle. If I have m numbers from 0 to 1, there'll be 2 that are 1 over m apart. And therefore, I can also write this. So this log m is going to be bounded by log of 1 over delta. Yeah. So I can certainly write this as an inequality depending only on delta, 1 over delta log 1 over delta times whatever I claimed. Okay. So if you don't worry too much about this log 1 over delta, I've proved what I wanted to prove. So then you can kind of analyze, well, why did I get this 1 over delta? This sum of exponentials is also known as the Dirichlet kernel. So it's something that you might have seen in a course of Fourier analysis, say, if you want to try to look at the partial sums of a Fourier series and see whether it converges to the function or not, then there's this pain of looking at the Dirichlet kernel, and the Dirichlet kernel is not an L1 function, right? And this log comes in exactly the same way. Okay? And you may also have seen a proof of Fayer's theorem, which kind of averages these partial sums, and then you get this thing called the Fayer kernel, which is nicely behaved, and for which is L1. Okay? So you can perform that trick in this argument and get something here that converges a little bit faster than the 1 over x, and then that'll be enough to give you a constant. Okay? Let me say how you can make that work. You have to handle a sum of this type. You want to bound this, right? Summing over all n in an interval from 1 to n. You can always put in some function here, phi of n over n if you like, provided phi of n is non-negative, always, and it's bounded below by 1 for when n is between 1 and capital N. Is that okay? So take any function phi that's non-negative and bounded below by 1. So instead of taking the characteristic function of the interval from 0 to 1, which is this guy and 0 everywhere, take some slightly smoother version of this. Right? Take this to be phi. Okay? Then when you carry out the argument here, you would get a phi here instead of just summing 1. Okay? So it's like the Fourier transform of this function phi evaluated at this point x. Right? And the smoother your function is, the faster the Fourier transform will decrease, and then you can make that argument precise. Then this log will just disappear, and you'll have the result as claimed. Okay, it's a technical thing, and not at all needed in any of the proofs that we did. Right? With the log is fine, it's just fine. Now let me give you a second set of arguments on how to prove this result. And then we'll stop and look at the applications of it next time. So what I have on the right-hand side is the L2 norm of this function s. Right? If I just integrate mod s alpha squared, I get the sum of mod a n squared. Now, if you have these well-spaced points, maybe another way to think about this is that the left-hand side here is some kind of approximation to the Riemann integral from 0 to 1 of mod s alpha squared. Okay? So if I can prove that, then this bound is saying that if the points are kind of not having much to do with each other, then this average does kind of behave like the Riemann integral, at least as an upper bound. Right? So can I compare? So the question is, can I compare the sum of to the Riemann integral right? So I have some function, some real valued function. I'm sampling it at some number of points, and I want to say that when I sample at those points, then I'm getting something that approximates the integral of that function. Okay? When would that be true? Well, of course, I need to take more and more points so that something like this is true. But also, even if I keep taking more and more points, I want to make sure that the function is not oscillating so wildly, right? That it's very, very specific which points that I pick. Okay? So that would say that I should maybe compare that what is really happening here is that I have some control over the derivative of this function as well, right? So you can think of, bounding a function. So let's say the simplest thing might be to take a function f on minus half to half. You can think of any in any other framework. And then you can say something like, well, suppose I tell you, can I understand what, say, f of 0 is? Can I give some kind of bound for this, maybe bound for the size of this, depending on continuous quantities involving the function f, right? So obviously, I should also involve the derivative of f in addition to f itself. If the derivative of f is too big, then you can't hope to prove something of this type. So, but you might expect to prove something like this, that this is bounded by maybe the integral of, so half. And then maybe something involving the derivative of f. Right? Assume that f is nice and once differentiable. Okay? And then this is actually an inequality that you can try to prove. Okay, so that's an exercise. How hard can it be? It's like an integration by parts argument. You play around with the derivative, do some integration by parts, and you'll be able to find the function f in terms of integrals involving f and its derivative. Okay? Now, once you have this, then you can imagine that I can understand some value of this function S alpha. Maybe by, or maybe of its square, let's say, or the square. Let me do it a little bit in 2 steps so I don't confuse myself. So if I perform a small dilation of this argument, I can say something like, I can understand a function at 0 by bounding it in terms of some small interval around it. So say it's from minus delta to delta, f of t dt. Maybe I should divide here by delta, right? It's like the average around the point 0 of this function, and then something involving the derivative from delta to delta. Is this okay? So check that some inequality of this type is true. It's the same inequality of this, like this, with a change of variable, right? Replacing f of x by delta times x. Okay. So now if I apply that, I'm going to use now if I use that, I can say S of alpha squared. I'm now going to be a little bit, forget about constants, and what I would write would be morally true, but you have to check some details. Maybe from so I should take the derivative of the square. So maybe it would be something like S of alpha plus x times maybe the derivative S prime at alpha plus x dx. Something like this. Okay? But now you see, if I have my points alpha 1 to alpha m that are delta well spaced, right? Maybe I should have done this with delta over 2 or something. Let's put delta over 2 here. then if I integrate in the intervals of length delta over 2, all the integrals that I have will be non-overlapping because the points are well spaced. And therefore, I would be able to say that this is now bounded by 1 over delta. Since these integrals are all non-overlapping, I can replace it by an integral from 0 to 1 of s of alpha squared d alpha. And now this guy will be a little bit different. It will be an integral again from 0 to 1 of s of alpha s primed of alpha d alpha. Right? Okay, but by Parseval we know what this is. This is the sum of mod a n squared. And use Parseval again here, first using Cauchy-Schwarz. So this will be bounded by the integral of s alpha squared times the integral of s primed alpha squared. And use Parseval on both of these. This will be a sum of mod a n squared. If you differentiate this, you'll get the sum of n a n quantity squared to the half. And that pulls a capital N out of the whole picture, right? Because n goes up to capital N. So in this argument, you get a 1 over delta from here, from this, and then you get some constant times n because of that. Okay? Which gives you, again, the same kind of results that I wrote down there, except that instead of a less than equal to, I get a less than less than. The implied constant in this argument is not 1. Okay, so that's two arguments proving this basic inequality, or both not proving this basic inequality, but both getting you some, some version of it, which is good enough. Okay, so then next time I'll give you applications of this inequality and what it means for characters, rewriting it in terms of multiplicative characters, and also why is this a sieve, which we haven't discussed yet. All right. In which one?
Is there a way to get rid of 1 over delta?
No, the 1 over delta is there in the theorem, right?
Oh, there is no log delta.
There's no log in this, yeah.
So in the second argument,
Yeah.
we would have to improve on using Cauchy-Schwarz in order to get the actual result. Just like in the previous argument, we would have to change out their summation.
Yeah, the second argument gives you a pi in front of the n, okay? Because of differentiating this e to the 2 pi I. And then you get some pi's out. And then, so it will be pi times n plus some constant over delta. I don't know offhand if anybody made a version of this argument getting the actual n instead of the pi. Other questions?